Hello, I'm Maureen Haberfeld. I'm the Lifelong Learning Coordinator of the Tallahassee Senior Center, and I'm teaching the Introduction to the Geology of the National Parks class that we've offered as a virtual lifelong learning class in the spring of 2020. And I'll just tell you a little about my background. I have a bachelor's degree in earth science from LaSalle University and a master's degree in geology from Texas Christian University. And in addition to being the lifelong learning coordinator at the Senior Center in Tallahassee, I also have taught as an adjunct professor of earth science and geology at Tallahassee Community College for 20 years. So let's get started with our class. Okay, this is just an introduction to geology as like a prequel class for our geology of the national parks, which is an 8-week class where we cover national parks all over the United States in different regions. So this is just to give everybody a little background on geology because I'm going to be referring to a lot of these things when I talk about the different parks. First of all, if you are interested in visiting a park or planning a trip, you probably want to go to the National Park Service website. They have all the brochures from the park, and you can read the brochures online. You can print them out, and each one has a section on nature and science, and you can actually read about the geology and the other science and nature that you're going to find in that particular park. So I encourage everybody to look at those in advance and can help you plan what you're going to do on your trip. There's also some websites from the United States Geological Survey that talk about the geology specifically of the national parks. So I want to refer you to those two websites, usgs.gov, and then this other one on, or I think it's the same website actually, on national parks. If you go to the USGS website, you should be able to navigate to that. This is the order of the classes in the National Parks class. This is the first class, which is just a basic introduction to geology where I refer to different parks that we're going to be talking about. The second part is parks with volcanic features and activity. Parks with surface water, weathering, and erosion. So that would be like parks in the Colorado Plateau, like the Grand Canyon, Bryce, Zion, and then parks with glaciers and glacial features, cave and reef parks, and complex mountain parks. Some of these classes take more than a session, so even though there's 6 classes here, there's 8 different sessions, 6 topics, but there's 8 different sessions in the course. We're going to start talking about rocks first, and our first park that comes after this class, the first group of parks are the igneous parks that have igneous activity. So igneous rocks are rocks that are formed from magma or lava. Some examples that you may have heard of are granite and basalt. We'll talk more about those. Sedimentary rocks are formed from pieces of other rocks. And some examples, common well-known examples of those are shale or mudstone, sandstone, and limestone. And then metamorphic rocks are rocks changed by heat and pressure from one type of rock to another. And some common examples of those would be the rock slate or schist, or the rock gneiss, where the G is silent, or marble. This is just a diagram, and there's lots of different ones. You can look some of these up, and this is just one I like on the rock cycle that shows, how basically each one of these groups of rocks can be transformed into another, and there's also shortcuts in between. So if you start with the igneous rocks, they're the rocks that come from molten magma or lava. Magma is actually the molten rock that's beneath the surface of the earth. Lava is molten rock that reaches the earth's surface. Basically the same thing. And as that molten material cools and crystallizes either beneath the Earth's surface or at the Earth's surface, you get igneous rocks. If those igneous rocks become weathered and then eroded, transported, and deposited as loose sediment, and then get lithified into rock, they can become sedimentary rock. Lithified means compacted and cemented together, the grains are, until they become, a rock, like sandstone or shale or something like that. And then if that sedimentary rock were to become deeply buried and subjected to intense heat and pressure, it could be metamorphosed into a metamorphic rock. And then any kind of rock can be melted again into magma. And you can also get igneous rock that gets metamorphosed. You can get metamorphic rock that gets weathered and eroded into sediment and becomes sedimentary rock. So there are shortcuts in between all the different parts of the rock cycle. So the word igneous means formed by fire. Igneous rocks are formed from, again, molten magma or lava that cools and crystallizes into solid rock. There are two types of igneous rock. The plutonic or intrusive igneous rocks form from magma that never reaches the Earth's surface, stays inside the Earth, thereby intrusive. Plutonic comes from the Pluto, who is the god of the underworld. So these rocks, the magma stays under the Earth and cools and crystallizes at depth. Volcanic or extrusive igneous rocks come from lava that actually exits the Earth and forms on the Earth's surface. So they cool and crystallize at the Earth's surface. Rocks that cool and crystallize beneath the Earth's surface from magma cool and crystallize at higher temperatures than rocks that crystallize at the Earth's surface. So the size of the crystals that you see in the rock is determined by the rate of cooling. And because there's deep in the Earth, there's higher temperatures, the plutonic rocks cool slowly. And because they cool slowly, the crystals have a chance to grow large. And so the rock is said to have a coarse texture because you can see the individual minerals. An example of that type would be the rock granite. Volcanic igneous rocks that form at the Earth's surface form by rapid cooling. So the lava cools at a higher temperature, so it cools pretty quickly. And the crystals don't have time to grow large. So instead you get microscopic crystals. And an example of that type of rock would be basalt, which has a very fine texture. You can't see the individual minerals. Looks pretty uniform. You can also get volcanic rock that cools instantaneously. Think about an example of maybe a lava flow flowing into water or something like that. And it doesn't have time for the crystals to grow at all. They cool instantaneously and form actually a volcanic glass, because glass has no crystals in it either. So there's no crystals. XLS is an abbreviation for crystals. And so examples of that would be obsidian, which you've probably all seen. Obsidian, it's usually black, but sometimes it has some white in it too. It's very shiny, looks like a glass, and it is glass. Or pumice. Those are volcanic rocks that have glassy textures. So here's some pictures so you kind of know what I'm talking about. Granite is the coarse textured igneous rock that cools from the intrusive or plutonic material, the magma. So it's cooling at depth where it's very hot. It cools slowly. So you see the individual crystals. That's why it's said to have a coarse texture. You see some white crystals, some pink, some black, and they're all interlocking. Granite can be different colors. It doesn't always have to be pink. This is an example of a basalt, which is the fine grained texture. The crystals are microscopic because this was rapid cooling from lava at the Earth's surface. So this is actually like a lava rock. And then here's your obsidian. It's a beautiful, shiny rock. Sometimes they make jewelry out of it. And they also used to use it to make arrowheads. Early people used to use it to make arrowheads. Sometimes they find these still. Okay, so we kind of divide up the types of igneous rocks into groups we call basaltic, the basaltic group. And that's named after the most common rock in that group, which is basalt. And they all have a certain composition. So the basaltic rocks tend to be dense, and they tend to be rich in iron and magnesium and lower in silica. These are all elements. And the most common example of that is basalt, which is of course fine grain, but there are also coarse grain varieties of this composition of rock. We won't get into all the names of those. One important thing, because we're going to talk about plate tectonics in a few minutes, is to remember that the oceanic crust is the rocks underneath the ocean are primarily made of basalt, which is a dense rock again, and that's going to explain some things in plate tectonics. Then we have the other group of igneous rocks we call the granitic rocks, named after granite, which is the most common rock in the group. These are less dense than the basaltic rocks, and they're low in iron and magnesium and higher in silica, particularly quartz, and that's a K for potassium, potassium feldspar, which is another type of mineral. And the most common example of that is granite, which we talked about granite as being coarse grain, but there are also fine grain varieties of this composition of rock too. And the continental crust, the rocks underneath the continents, are primarily granitic, while the rocks underneath the ocean are primarily basaltic. And so if you remember that they're denser than the oceanic rocks are denser than the continental rocks. That helps explain some things in plate tectonics. Here's a picture of a basaltic lava flow in Hawaii Volcanoes National Park on the Big Island of Hawaii. And then there's granite, which is in El Capitan in Yosemite National Park. So there's a couple of national park examples of where we have some of these igneous type rocks. This is just a chart that shows classification of igneous rocks. And they're classified by both their composition, which we just talked about, and their texture, whether they're fine or coarse grain. So you can see that, you know, there's several types of the granitic type of rock, coarse and fine grain varieties. There's also intermediate composition igneous rocks, and then there's several types of the basaltic type of igneous rocks, and then there's other types too. So granite and basalt are not the only types of igneous rocks. They're just the two most common, the ones you hear about the most. Okay, now we'll talk about sedimentary rocks. Sedimentary rocks is the second type, the second group, and they're formed from sediment, which is weathered products, and they're formed at low temperatures compared with the igneous rocks, which are formed from high temperatures, hot molten rock material. These are formed near the Earth's surface at low temperatures. And sedimentary rocks make up 75% of the outcrops that we see on the continents. And that makes sense because they are formed at or near the Earth's surface. They tend to stay near the Earth's surface. So most of the rocks we see are sedimentary. There's a couple of different types of sedimentary rocks. The first type we're going to talk about is detrital or clastic. They're synonyms, sedimentary rocks. And these are sedimentary rocks that are products of mechanical weathering, which is the physical breaking down of rock material. Some common detrital or clastic sedimentary rocks include shale or mudstone, which is the most abundant one, siltstone, sandstone, and conglomerate. And they're actually classified by their particle size, the shale being the smallest particles, has clay size, and then they get a little bigger with the siltstone, a little bigger, and then the conglomerate has the biggest particles. There's a picture of shale. Sedimentary rocks tend to have fossils because, again, they form at or near the Earth's surface. Shale is also called mudstone because it forms from mud. And you can certainly envision because you've probably all seen this, a leaf from a plant or a piece of a plant falls into the mud. And so it will get buried and preserved as a fossil. So that's a fossil, plant fossil in shale. Here's a sandstone. You've all seen sand on the beach or in dunes. So that's just sandstone that is formed from sand that gets lithified and hardened into rock. And then that's a conglomerate, has bigger particles. The other group of sedimentary rocks are chemical sedimentary rocks. And these are products of chemical weathering. They come from minerals that were in solution in water. And then the water evaporates and they precipitate out to form sediment. They precipitate out of the water. The most common rock in that group is limestone. If you're from Florida, you live in Florida, you probably have heard of limestone because limestone is the most common rock in Florida and it makes up most of our Florida peninsula. And chemical sedimentary rocks are distinguished by their mineral composition. Limestone is primarily composed of the mineral calcite, calcium carbonate, CaCO3. There's a limestone that has fossils. The process that transforms loose sediments into solid rock, the name for that is lithification. The root of that word, L-I-T-H, lith, L-I-T-H, lith, that means rock. So lithification is transforming those loose sediments like the sand or the mud into solid rock. And that happens by the process of compaction. All of that material gets squeezed together by other stuff being deposited on top of it, and then cementation. And that usually occurs by water in the environment. Water always has dissolved minerals in it. If you notice, sometimes you have to clean around your faucet because it gets like a little, or around, maybe your water faucets and your sinks, get a little deposit of white material. That's calcium carbonate. That's calcite that's dissolved in the water. And pretty much all water has minerals dissolved in it. And if the water evaporates away, it leaves a deposit of that. So you can imagine that happening around the grains of sand or clay. And that's how the cement gets around it. And between the compaction, the squeezing together, and then the depositing around the grains, the rock will get lithified and cemented together. Some common features of sedimentary rocks include strata. That's that the rocks are in beds or layers. And if you think of the Grand Canyon, most people can picture that in your mind with the layers of rocks. Those are strata. They also tend to have fossil. Sedimentary rocks are the type of rock that generally has fossils because you could imagine if something falls into hot lava, it's probably not going to survive and become a fossil. And the same thing with the heat and pressure of metamorphism. Usually does not preserve any fossils that were in the rock unless it's very low grade metamorphism. So there's your strata in the Grand Canyon. You see the different layers of rocks. Sedimentary rocks are formed in flat-lying strata, the oldest layers on the bottom, and they get progressively younger unless they've been deformed. The third type of rock are metamorphic rock. And metamorphic rock are changed rocks that formed from heat and pressure acting on pre-existing rocks. And the degree of metamorphism shows up in the texture and the mineralogy of the rocks. So there's two types of metamorphism. There's low-grade metamorphism, where the rock is only slightly changed. So, for example, shale, the rock shale, the sedimentary rock shale to the metamorphic rock slate. They look very similar. The shale is just a little harder. It's got a little shinier. It's just been, I use the example like cooked or baked. It's just been cooked or baked a little bit. So it's not changed much from the original rock. And then higher grade metamorphism, it doesn't look so much like the original rock. So if you go from shale to slate and then it undergoes more metamorphism, it may become the rock schist or gneiss. It doesn't look anything like the original rock shale. So it's just how much metamorphism has occurred to the rock. The agents of metamorphism, the most important one is heat. I always like to say it cooks or bakes the rocks and recrystallizes the minerals and causes the most change. Also pressure, that's the second most important metamorphic agent. And then chemically active fluids, ion exchange that occurs. Metamorphic textures there's certain textures in rocks that are characteristic of metamorphism, and that is called foliation. And that's when minerals in a metamorphic rock are lined up in parallel alignment, and that's actually perpendicular to the direction of the force. We'll see a picture of that. Some examples of foliated metamorphic rock are slate, schist, and gneiss. And then some metamorphic rocks, particularly ones that only have one mineral in them, like marble or quartzite, are not foliated because there's not minerals to line up. So this is an example of foliation. This is a granite, a black and white granite, which is an igneous rock. If it gets undergoes a high-grade metamorphism, where you get a lot of heat and pressure, the pressure will cause the minerals, which are just randomly dispersed here, to line up in parallel alignment. And so there you get your, that's what foliation is. It looks kind of like stripes, black and white stripes. The Appalachian Mountains are an area that is highly metamorphosed. And the metamorphic rocks are eroded and folded. This is a radar image of the Appalachian Mountains. But if you've ever driven up like I-75 from Florida north, you know, up to the north, you can often, when you get up into the mountains, you know, especially in the Smokies and, you know, the Shenandoah, you can see a lot of this, you know, folding even on a small scale in the rocks. And that's from metamorphism. So these are some of the rock names. This is just a chart that talks about metamorphism and some of the rock names. And then the original rock, they often call the original rock the parent rock. So, you know, shale or mudstone or siltstone might become the metamorphic rock slate. And then with increased metamorphism, these are higher grade metamorphism as you go down. And these are foliated. And then down here, these rocks have pretty much one mineral in them, so they're non-foliated. You can't see the banding. I want to mention now the geologic time scale, because as we go around the United States talking about the different parks, we're going to be talking about the ages of the rocks in the park. So I'm going to be mentioning some of these you know, units on the geologic time scale. The geologic time scale subdivides the Earth's history. The Earth is about 4.6 billion with a B years old, and it divides that into many units. And it was created using relative dates because it was created in the 1800s in England. They did not have the ability back then to do radiometric dating, which gives you an accurate absolute date on a rock. They couldn't do that back in the 1800s. They could just tell which was older and which was younger by which was on top and which was below. So it was created using relative dates, which is just saying which is oldest, which is youngest. The bottom part of the geologic time scale is called the Precambrian, and that's the oldest part. And actually it's all squished down into the bottom, and it represents, even though it represents 85% of the Earth's history, it's never drawn to scale. Usually when you see a geologic time scale, it's all squished down in the bottom. And it's because we don't have a lot of Precambrian rocks that we can study on the Earth's surface. So we don't know about it that much. And also there wasn't much life back then, basically just like some algae and things like that. So they don't have a lot of fossils to study it either. So we, from the Cambrian on is what we mostly focus on in the geologic time scale. Precambrian was 4 billion years prior to the Cambrian. So we're really just looking at about the last 500 million years or so, most of the time. It's not subdivided into smaller time units because the events of the Precambrian history are not well known, and they don't know a lot of details about them. We know a lot more about from the Cambrian on, the last 500 million years. The first, and like I mentioned, the first abundant fossil evidence does not appear until the beginning of the Cambrian. So that's when they can study it a lot better, when they have the fossils. So here's a geologic time scale. And again, this is like over 85% of Earth's history, but they've squished it down into the bottom, the Precambrian. And then it's divided, above the Precambrian, it's divided into 3 eras: the Paleozoic, Mesozoic, and Cenozoic. And then they subdivide some of these even further. But the Paleozoic goes from the Cambrian to the Permian. And throughout this course, we're going to be talking about you know, rocks that were formed in the Permian Basin, and we're going to talk about some Mississippian rock. So we're going to be referring to these ages a lot. And then, of course, the Mesozoic era, that's the famous age of the dinosaurs. And there's the Triassic, Jurassic, Cretaceous. And then the Cenozoic era is the most recent one, and that goes from the Paleocene to the Holocene. And we'll be talking about some of the glacier parks and, you know, some of the glaciation that occurred in the Pleistocene, which is very recent geologically. Also mention that there were large mass extinctions at the between the Paleozoic and the Mesozoic, between the Mesozoic and the Cenozoic. There are big mass extinctions in these, and we'll mention some of those later too. Okay, now I want to get into plate tectonics. Because plate tectonics is the you know, the theory that explains how the Earth works. And so you definitely want to have a little bit of an understanding about that, since we're going to be referring to this too when we refer to how some of the different parks were formed. So plate tectonics is associated with the area of the Earth, like the outer part of the Earth, called the lithosphere. Again, remember, lith is rock, so the rock sphere. The lithosphere consists of the crust of the Earth, which is the thin outer skin, and then the very, very upper part of the mantle that is still hard and solid rock. So those put together are the lithosphere. And the plates are in the lithosphere. So we call them lithospheric plates. So the Earth consists of about 20 of these lithospheric plates. 7 of them are large or major plates, and they move slowly a few centimeters a year. The largest of these plates, and some of the plates are beneath the ocean, some of them are on the continents, some of them are, most of them have both oceanic and continental material on them. The largest plate is the Pacific plate. And probably you've heard of the Ring of Fire. The Ring of Fire is like the boundary of the Pacific plate. Most of these plates are actually beneath the oceans. And the mechanism is unequal heat distribution within the Earth, the mechanism that moves them. So the whole Earth consists of these lithospheric plates, which are moving. So this is kind of just what I said. The Earth's crust and uppermost mantle is a cool, rigid, solid layer known as the lithosphere. And the lithosphere is where the plates are, so we call them lithospheric plates. And then the lithospheric plates ride on top of the weak plastic layer of the mantle known as the asthenosphere. The rigid lithospheric plates ride on top of that weak plastic asthenosphere. And if you think of the lithosphere as being like hard and solid, like a rock, and think of the asthenosphere as being something like a putty, something like silly putty or something underneath a rock, the lithospheric plates move on top of that putty-like layer. It's not liquid, it's more like plastic, like a putty. So the rigid lithospheric plates move on top of the weak plastic asthenosphere. So again, lithosphere, cool, rigid, solid, tectonic plates that float on that plastic asthenosphere or asthenosphere. And large-scale geologic features occur at the boundaries between these plates. Things like volcanoes, mountains, trenches, earthquakes occur there. They're very common at plate boundaries. So this is a plate map, and they're a little different than looking at maps that we're used to looking at that highlight the land. So these different colors represent the plates. So I mentioned the largest plate here is the Pacific plate, and that is underneath the Pacific Ocean. And then there's a few smaller plates also underneath the Pacific Ocean, like the Nazca plate and the Cocos plate. And then here's the North American plate, this greenish, bluish greenish one here. And you look at what's on the North American plate. The North American plate carries North America, so it is named for something that it carries, but that's not the only thing. Part of the Atlantic Ocean, part of Greenland, half of Iceland, and then part of the Pacific Ocean up here, you know, below Alaska, and a little bit of Russia is all on the North American plate. So geographic the plates don't care about geographic boundaries, countries, things like that. They are, you know, geologic boundaries. So, and then the gold is the Eurasian plate. There's your pink South American plate, and this bluish one here is the African plate. This little purple one's the Arabian plate. There's a little tiny plate up here called the Juan de Fuca plate, which is a small sliver of a plate that's separate from the Pacific plate, but underneath the Pacific Ocean. And this is subducting, we'll talk about that in a minute, under the North American plate. And it's responsible for our Cascade Mountain range that we see, where we have Mount Rainier, Mount St. Helens, a number of our nice national park areas, Crater Lake. And then you'll notice here the Nazca plate right here, this small plate, is also under the Pacific Ocean. It's subducting under South America, and that helps create the Andes Mountains. So these definitely are, you know, related to mountain building. If you look at volcanoes and earthquakes and relate them to and draw them on a map, you definitely can see that they are defining the plate boundaries. You can draw the plate boundaries. Basically, here's that Nazca plate I was just showing you. You can draw those using the plotted volcanoes and earthquakes around the world. Now, they're not all on plate boundaries. You'll notice there's some anomalous ones that are in the middle of plates, but they tend to cluster around plate boundaries. So, you know, here's your ring of fire. So there are three types of plate boundaries. There's boundaries where the plates are moving apart, and those are called divergent. They're diverging or moving apart. There's boundaries where they're coming together, and there's three subtypes of those. And then there's boundaries where the plates are just passing each other like that. And the coming together ones are called convergent. The ones that pass each other are called transform. And they show you the different types of plates on this slide here. I encourage you, if you want to learn more about the plates, there's a couple of YouTube videos, and seafloor spreading is what you get at your divergent plates. So you can look up this video on seafloor spreading on YouTube. You can just search for seafloor spreading. There's a number of videos there, and it'll explain more what happens at a divergent boundary where the seafloor is coming apart. And then the convergent boundaries, there's three types. And at two of the types, we get what's called a subduction zone, where one plate is going under another. And there's also YouTube videos on subduction zones. So if you're interested in watching that, you can watch some of those. I'm not going to put it on right now. So most earthquakes, volcanoes, and mountain building occur along plate boundaries. And it basically explains a lot of the earthquakes, volcanism, and mountain building that we have on Earth. There's also a really good, it's very long, YouTube video called The Ring of Fire, about the Pacific Ring of Fire. And, you know, if you're interested more in the volcanism and earthquakes along the Pacific Rim, you might want to watch this. It's very good. But I think it's about an hour long. It's called Ring of Fire. Many of our beautiful national parks were formed along plate boundaries. So we're going to talk about some of the igneous ones first, and some of those are the plate boundary parks. Yosemite National Park, for example, is at a subduction zone with an oceanic continental convergent plate boundary. And the three types of convergent plate boundaries depend on the types of plates that are coming together. If there's an oceanic plate and a continental plate coming next to each other, converging, then we call that oceanic continental. If there's two oceanic plates converging, we also get subduction. We call that oceanic. And if there's two continental plates converging, that's continental. And where there's an oceanic plate involved, you have subduction. Oceanic continental, the oceanic plate's going to subduct. If you have two oceanic plates, the denser one will subduct or go under the other. And at subduction zones, you get your earth material being taken back into the mantle, plate material, lithosphere taken back into the mantle. At divergent boundaries, new lithospheres being created. So the subduction zones actually recycle the lithosphere, because otherwise if you didn't have that recycling process, the Earth would be growing larger and larger all the time if you had these, divergent boundaries creating new lithosphere. So it's not growing larger. So there's places where it's recycled, and those are subduction zones. Mount Rainier is at an oceanic continental convergent plate boundary that's actively active today. The one in Yosemite is no longer active. So we're going to talk about all these in more detail in following classes. Denali National Park in Alaska is an oceanic continental convergent plate boundary also. Now, if you look at the east coast of the United States, Shenandoah National Park, that is formed from a continental convergent plate boundary. And that's where no recycling of material occurs, no subduction. So instead, everything gets crumpled up into mountain ranges. Smoky Mountain's the same thing. It's part of that Appalachian Mountain Belt, continental convergent. Now I want to talk about some geologic structures that we're going to be, referring to when we talk about our national parks. There's a couple different kinds of deformation you get in rocks, and that's the change in the original shape and size of a rock body. And you can get elastic deformation, where a rock will return to its original size and shape, just like with a rubber band. If you pull a rubber band, even if you snap the rubber band and break it, it will go back to its original size and shape, except where you have that little break. So that's what happens to rocks. You don't usually think of rocks as being elastic, but when they get buried with a lot of heat and pressure, they do behave elastically, surprisingly, but they do. You can also get ductile deformation in rocks, and that's this change in size of shape without fracturing. So that happens in very high temperature and pressure situations where you get like folding rocks. And then you can get brittle deformation where the rocks fracture. And that happens at lower temperatures and pressures. And that's where you get faulting or, fracturing of the rocks. So let's talk about folds first. Folds tend to form from compressional forces. If you take something like this magazine and you push it together and you compress it, it's going to form a fold. And the same thing happens much more slowly with rocks. This part is an upfold and this part is the downfold. So the upfold is called an anticline, or upfold or arch part, and the downfold is called a syncline or a trough. Faults or fractures in rocks occur where displacement has taken place and they've actually had brittle deformation. And there's different types of faults. There's depending on which side has moved up or down. Normal, reverse, thrust, or stripe slip. I'm not going to talk about all of those in detail. I do want to show you some folds. And again, we get a lot of these we see a lot of these in the Appalachian Mountains because that was a continental convergent plate boundary when Pangea was together. So here's your upfold or your anticline, and then your downfold or syncline. That's the arch, and that's the trough. This is a picture of a real anticline in rocks somewhere in the Middle East. And these are some of your different types of faults. That's a normal fault, and that is from pulling apart forces where this block is down relative to that block. And then that's a reverse fault from compressional forces where one block gets pushed over another. That's in real life, real outcrop. That's a picture of a normal fault. Then the technical term that they use in geology for mountain building is the word orogenesis or orogeny, and that's the process that produces a mountain belt. And that includes all these things we were just looking at: folding, faulting, metamorphism, and igneous activity. So compressional forces produce that folding and also faulting where you get one block pushed up over another, igneous and metamorphic activity. So mountain building is associated with convergent plate boundaries and also oceanic continental convergent boundaries like we have in the Andes. And what happens here with a mountain building with a convergent boundary, oceanic continental, is you have a subduction zone. And again, the denser oceanic crust, which is made up of basalt, is going to be subducted underneath the less dense continental crust, which is made of granite, remember, which is less dense. We talked about that a little bit while ago. And so the denser oceanic crust is always pulled under the continental crust. And you get a subduction zone. You get a deformation of the continental margin right next to the zone. The rocks get deformed. And then you also get, as the subduction gets deeper, the material that's getting recycled starts to melt and form magma. And that works its way up and forms a volcano. So further inland on the non-subducted plate, you get a volcanic arc mountain range. In the continental margin, where you're getting the deformation, you get something called an accretionary wedge. And in that area, the sediment from the subducting plate that goes down under the other plate, sediment from that's going to get scraped off and pushed up onto the non-subducting plate. With my students, I always use the example. If you take one hand, if I took my left hand and I smeared it with peanut butter, I've never actually done this, but you can imagine if I smeared it with peanut butter and I pushed it underneath my right hand, what would happen to the peanut butter? It would mound up on the edge here. So that's an example of what happens with an accretionary wedge. It accretes or adds on and piles up right here. And that forms one mountain range. And then as the rock gets subducted deeper into the mantle, it starts to melt. That melted material moves its way up and forms further inland on the non-subducted continental plate a volcanic arc. So you get two parallel mountain ranges, one from the accretionary wedge right on the edge, and then one further inland on the from the volcanic arc. That's what happens with an oceanic continental plate boundary. Accreted means it gets added to the overriding crustal block. So here's what you have. Here's a picture of it. First you have these two plates, and then you get the subducting oceanic lithosphere. And as that's subducting, material from the top gets scraped off like the peanut butter and gets accreted or added on to the overriding continental plate. And so this gets deformed into a mountain range, a coastal mountain range right here, as you're going to have the water right here. And also you get a trench, a deep sea trench, deep ocean trench, which is underneath the water at a subduction zone. And then further inland, as the material gets drawn back farther, subducted more into the mantle, it gets hot, heated up, it melts, and it moves its way up through and burns its way up to the surface and creates volcanoes. So that's your continental volcanic arc. That's your other mountain range. So you have the accretionary wedge and the continental volcanic arc, two parallel mountain ranges at an oceanic continental convergent boundary, or an Andean type. So you have at the Andes Mountains. Now I mentioned that Yosemite was an example of one of these. And Yosemite is actually an old eroded one. Here's the Sierra Nevada mountains, which are, where Yosemite National Park is located, is an eroded volcanic arc. What you're seeing is everything's been eroded off the top. So you're actually seeing the granite there is the magma chamber. It's been uplifted and eroded. So you're seeing the core of the volcanic arc. And then the coastal range was the accretionary wedge sediments that got formed, into the coastal range of California. So there's your Sierra Nevada, which was at one time the granite was a magma chamber. When you get two continents converging, continental convergence, you don't get any subduction because remember, continental crust is not dense. It's not dense enough to subduct. So instead, everything crumples together and forms into high mountain ranges. On Earth today, the youngest mountain range is the Himalayas, and that's where India has geologically pretty recently collided with Asia and formed the Himalayas. The Appalachians formed a lot longer ago, like the end of the Paleozoic. And so the Appalachians are old and eroded, but they used to be as high as the Himalayas, they believe. But again, you get no subduction here. So that's another way you can get mountains with continents converging. We talked about oceanic continental convergent boundaries like the Andes, and that's one way we get mountains. Another way we get mountains is when two continents converge. And that examples of that would be the Appalachians and the Himalayas. And then we can also get something called continental accretion, and that's with plate tectonics, where a plate will carry a small fragment of a crust and push it up onto a continent. For example, we have the Aleutian Islands off the coast of Alaska, and up near where they are, the Pacific plate is subducting under the North American plate. In many millions of years of those Aleutian Islands get pushed up onto the continent, onto the land of Alaska, that would become continental, that would be accretion. And their geology would not match the rocks that were already in place. So those are called terrains. Terrains in geology, and it's spelled differently than the word T-E-R-R-A-I-N, which means like land. This is T-E-R-R-A-N-E. A terrain is a part of the crust that's been added on to somewhere else. So it means it's been accreted. So it's a block, an area that you find with a distinct geological history, different from the adjoining areas. And they're very complicated. The whole west coast of North America, all the way from Mexico, all the way up to, Alaska, is composed of many, many, many different terrains. I did my master's thesis on West Central Nevada. I mean, that's just one little tiny area of all of these, areas, and, very, very complicated geology where, plates movement has pushed, rocks into areas, with a different history. So the whole Pacific coast of North America is these terrains. Lots of, master's thesis and PhD dissertations have been done trying to figure this all out. So here is what's happened with continental convergence, where India, if you look at India 70 million years ago, it was down here, and it has slowly moved up towards Asia, and it has been collided with Asia, continental convergence, and through that it built up the Himalayas, so the Himalaya mountains. And so there is no more subduction. Now, before this happened, the ocean basin was in the middle between the two continents, between India and Asia. Well, all of that oceanic material got subducted. So there is a remnant subduction zone under here. But once the two continents collide, subduction stops. So again, terrains and mountain building. Prior to terrains being accreted onto the continent, some of them may have been mini little microcontinents, island arcs, submerged fragments of crust that were pushed up, extinct volcanic islands or plateaus under the ocean. So all these things, make up our west coast and make it hard to figure out. As oceanic plates move, they carry these embedded, little micro plateaus or different island arcs and things, and they are not subducted, they are added on to the crust. So that's showing you accretion of an island arc. It's carried, the island arcs here, it's carried by subduction, but then when it gets up to near the continent, it gets pushed up on here and creates some complicated geology. So this is the entire showing you the entire west coast of North America. Like I said, from Mexico all the way up to Alaska is made up of all these different terrains. So it took a lot of geologists doing a lot of work to figure all this out. And the red is island arcs, the yellow is submarine deposits, blue is ancient ocean floor, purple is displaced fragments of continents. So, you know, very, very complicated geology in the western part of the United States. Okay, so we are finished with our first session, just introduction to geology. So I hope that you learned something from this, and if you want, you can watch the whole series and learn all about the geology of the national parks. Thank you so much. Bye.